this video, I want to talk a bit about mass moment of inertia. So mass moment of inertia is a property of a rigid body that gives us some idea of its resistance to rotation. So it's going to be important for us when we analyze dynamic systems and want to think about their rotation and how we influence that through the application of moments and torques. So we come to the mass moment of inertia from our basic equations of motion. So we can recall from before that we have the summation of forces equals the mass times the acceleration, and the summation of moments equals I alpha. So mass, of course, is m, acceleration is a over here in this in the first equation. In the second equation, we have mass moment of inertia and rotational acceleration. So these two quantities kind of mimic, in a rotational sense, what we already have going on in the linear or directional sense of F equals ma. So if we take a generic rigid body and we say that it's going to rotate about some axis, so it's undergoing rotation, and we want to figure out, what the resistance to that rotation is, how much torque we're going to have to apply for a given mass. We can treat this this rigid body as a collection of small little, discrete units of mass. So I might have a particle located here, a particle located here, a particle located here. And so all of these are little quantities of mass. So for each of these masses, if I label them, let's call them M1, M2, M3. And we're going to measure then how far away each of these masses is from that axis. So we're going to measure that perpendicular distance and label those R1, R2, and R3. So for any one particle, one of those little differential units of mass, I can calculate its contribution to the mass moment of inertia via the equation r squared delta m, where delta m is that little differential unit of mass. So I'm multiplying r squared by m. We can see, looking at this, that we're going to have units of kilograms times meters squared, or pound foot squared, or slug, here I'm talking pound mass, slug foot squared. So we can kind of see what our units are so that we can use that when we work with it later. And if this is the equation for just one mass particle, then we should be able to see that we can calculate the net mass moment of inertia for the rigid body by simply summing all of these little contributions of mass. Now, we also know that the summation of these little differential units of m can also be expressed as an integral of r squared over the mass. That's great. We've got a formulation for it, but really it's more practically useful, especially in a course such as machine component design, to apply this to kind of some standardized shapes, because most of our machine components tend to be relatively standard shapes. So most textbooks will provide example expressions, and we can go ahead and look at some examples. So starting with a slender rod, and the terminology here is important. Calling it a slender rod is basically saying that it's much longer than it is in the length dimension than it is in the diameter dimension. So really what we're saying is, like, the diameter contributes negligibly to the mass moment of inertia, and instead we're focusing on the length. So if we have this slender rod of length L, and it's oriented on a coordinate axis system, we'll put y in that direction. We'll say it's aligned parallel with the x-axis, and then the z-axis is like this. We can calculate the mass moment of inertia. But now the key thing that we need to consider here is that the mass moment of inertia is going to be different depending on which axis I'm rotating around, right? So my geometry and my physical interaction changes whether I'm saying that it's going to rotate like this around the y-axis or it's going to rotate like this around the x-axis. Those are two very different situations. So for this long slender rod, rotation around the x is going to be approximately equal to 0 because we've said that it's relatively thin, and under that assumption it doesn't really have much resistance to rotation in that direction. If we look at rotation about the y and z axes, so that would be like this and then like this, using my pen here as a tool, we can see that those are symmetric, right? There is no difference because the rod is rotationally symmetric, and therefore rotation about these axes is the same as long as that symmetry is true. So in this case, then we can write Iy is equal to Iz, and the equation for this then is 1/12 ml squared. Another example shape that we might find useful would be a rectangular plate. So coming up with a little drawing for that. And if we say that our coordinate system for rotation in this case is going to be located in the center of the plate, and the x-axis is perpendicular to the face, normal to the face of the plate, then we can define some things. First, define our geometry. And in this case, then, we can write these equations and think about rotation about these axes. So first, rotation about the x-axis. Rotation about the y-axis. And rotation about the z-axis. Now you might ask then, well, why haven't we included any terms for the thickness of this plate? Well, for this rectangular plate, our assumption is that the two dimensions B and C, as they're labeled here, are significantly larger, again, than whatever that thickness might be, and therefore we're neglecting that contribution from the thickness. All right, lastly, we're going to do a cylinder. Let's rewrite that a little better. And the cylinder, as you might expect, is going to look similar to our long slender rod. But of course now we're arguing that the diameter, or the radius of the cylinder, radius let's call it in this case, labeled A, is no longer a negligible quantity. So it's relatively significant and therefore needs to be considered. Of course, our long slender rod is an approximation of a cylinder. And if we really want to be thorough or be complete, we can just use the cylinder formulation rather than skipping ahead or skipping to a long slender rod formulation. So under this expression, we now have Ix equals 1/2 m a squared. We still have rotational symmetry between the y and z axes. But we get some slightly different equations if we go back and compare this against the slender rod example. But of course, we can see that if we take the radius a and take it to 0, our equation works out to be the same as for our slender rod example. All right, so there's a lot of other possible equations that we could pull from a textbook and use as a lookup table in a textbook and things like that. We'll find that we can combine these various shapes that we have common equations for, and through superposition apply those together in order to get slightly more complex shapes and geometries. And we'll see how to do that as we work through example problems. All right, thank you.